Welcome all to the last section of chapter 12. This section is about relative motion analysis of two particles using translating axes. These are two examples where relative motion of two particles using translating axes is used. So if you, for example, look at the left-hand side, you will see that the motion of the ball B, if it is described by the particle, which is the person over here at A, then we need to use this principle because A is actually moving. So if we fixed a coordinate over at point A, then point A is actually moving. This is translating observer. The same thing goes with the example on the right-hand side. So here we have two boats. One of them is moving in this direction and the other one is moving in this direction. So in any case, if the observer in boat A is trying to measure the velocity or acceleration of boat B, then again the relative motion has to be considered because A is not fixed. A is moving. So this is going to be a translating basically coordinate system or translating observer. So this is why we need to use the relative motion. Now let's set up the first kinematic relation, which is for position. And if we consider this example, what we have over here, we have a fixed observer. So at point O, this is an observer, but this observer is fixed. So the observer at point O, the origin, can have a measure of the translation of object A, which is this person, or this particle B. And any sort of measurement made by observer O has to be absolute. So this is why the position vector going from observer O all the way to A, we call it RA as a vector, the position vector RA. Again, this observer will measure the absolute position of particle B. And this is why the position vector is called RB. However, if the person who is treated here as a particle, as we explained earlier in chapter 12, is moving along this path, and he wants to measure the velocity or the position or acceleration of particle B. Now, this person is moving, and this is why we call the coordinate system attached to him X bar, Y bar, Z bar. So it's a different coordinate, and this different coordinate system, this is what we call translating observer because he is translating. Now, if this observer shoots an arrow, a position vector, toward B to measure its position, then that arrow has to depend on the position of A, because after 1 second, position A will change, after another second will change. So at every moment, the position of B has to be measured relative to the position A, and this is why the position vector is written in a relative form. So in summary, the position R, let me just make this one a bit clear. So the position RB as a vector is equal to the position of A plus the position of B relative to A. It's a vector notation. And all what we did is we added vector in a simple way. This vector B sorry about this. So this RB is equal to this vector plus this one. That's it. So here, again, just a quick summary. We call the position of A and B as absolute position, while the position of B relative to A is a relative position. It's not absolute. This is why if we want to measure this relative position, let me just, then it is RB with respect to A is equal to RB minus RA. So here we have let's have a quick example. If RB is equal to 10I plus 2J and RA is equal to 4I plus 5J, then RB with respect to A is going to be equal to 6I minus 3J. How I get that? Well, we already said that RB with respect to A is equal to RB minus RA. So I have 10I plus 2J minus 4I plus 5J, which clearly, if I take 10 and I subtract 4 from it, I get 6. And if I have 2 and I subtract 5 from it, I get minus 3. What is important over here is to note something. So note that RB with respect to A is equal to minus RA with respect to B. If we want to finish the kinematic relation for relative motion, then basically we start with RB with respect to A, the position, equals to RB minus RA. Simply, if I take the derivative of the position vector with respect to time, I will get VB with respect to A equals to VB minus, sorry about this, VA. Similarly, I can say that the acceleration of B with respect to A equals to AB minus AA. What you need to note is that this is a very important keyword. This is a translating observer. So in the next chapters, we will see that those equations are not the same if the observer who's translating and who is moving happens to be translating and rotating. The story is totally different. So this is only for translating observer. As we saw from the previous examples, we will always end up having 3 vectors added together. So in this regard, the sine and cosine laws are very useful. So let me write them down here. So the sine law is basically relating the length A over here with the angle A, sine A, to other part of the triangle, which is B over sine B, which is equal to C over sine C. Now, the cosine law is written like this. So A squared, which is the length of the arm A, is equal to B squared plus C squared minus 2BC cosine A. Similarly, B squared equals to A squared plus C squared minus 2AC cosine B. and c squared equals to a squared plus b squared minus 2ab cosine c. So let's have this example where we can see that there are two cars, car B and car A. And at one instant, car B was moving with speeding with a velocity of 18.5 meter per second along this line and acceleration of 2 meter per second square. But car A was speeding at an acceleration at point A, at a velocity of 10 meter per second and a tangential acceleration component at this point of 5 meter per second square. So the car A is moving along a curved path, which happens to be a quarter of a circle, which has a radius of 100 meter, and the position of point A is determined at an angle of 45 degrees. What we want is to find the relative velocity of A with respect to B, as well as the acceleration of A with respect to B. Now, let's start writing down the velocity equation, the absolute velocities, in vector notation. We will start with VA. So for VA, if you look carefully, the vector is pointing downward. This is 10 meter per second. And if I want to draw the coordinate system over here, then this is the x positive and this is y positive. So basically I can have two vector, positive x and negative y, to represent the 10 meter per second, which means VA is equal to 10 cosine 45I minus 10 sine 45j, which is equal to 7.07I minus 7.07 j meter per second. Now VB, since it's moving in a straight line and in the right direction, so we are going to have it as 18.5 I meter per second. Now to calculate the relative velocity, which was requested, VA with respect to B, then this is basically equal to, and by the way, sorry, I forget to write down the arrows over VA and VB because they are vectors. So we're going to get VA minus VB, which is equal to 7.07 I minus 7.07 J minus 18.5 I. And what are we going to get? We're going to get minus 11.43 I minus 7.07 J meter per second. Now, if we want to get the magnitude, then we need to square each component under the square root, which is 11.43 squared. We just, did not write the minus sign because the square of the sign is just positive, plus 7.07 square. Again, we did not put the minus sign since its square is positive. So what we are going to get, we're going to get 13.4 meter per second. Now, if we want to know the angle theta, then it is equal to the tan inverse of the y component, which is 7.07, divided by, so even if you put the minus sign, they will cancel out 11.43, which is going to be 31.73 degrees. Now, if we want to represent this angle, you just need to look carefully over here, which is, this is the positive x, this is the positive y. As we showed, the VP is actually going in the positive x, while this one is going in an inclined angle. So if I want to show this, I will show 18.5, a long arrow, so this is VB. And then I will show the 10 meter per second. It has to be a little bit smaller. This is VB. Now, the relative vector is going to be this one. This is VA with respect to B. Now, let me draw this again. If I draw this again, and I have VA with respect to B, then this vector is composed of two components, negative x and negative y. Is that right? This is actually what we got. We got negative I and negative j. The angle is measured here. That's the angle, which is actually supposed to be theta. So this is actually theta. So that angle is theta. And clearly, this angle is measured from the negative x downward like this. This is theta. Now, let's write down the acceleration equation. And we will start with A, because A has two components. One of them is for tangential, one of them is for the normal. So in order to do that, we need just to make a quick sketch over here. So let's say this is point A, and this is the curvature. Now, what will happen is that the tangential component will go like this. This is AT, and what we have also the normal component, AN. Now, you know that both of these components are perpendicular to each other, and they're basically x and y component, or I and j, is as follows. This one will have an I component in this direction and a j component in this direction. This one will have an I component in this direction, a j component and an I. The angle here is 45 and the angle here is 45. So, and we have also been given the tangential component. This one was 5 meter per second. It was given to us. The normal component, AN equals to V square over rho. So here, V is 10 meter per second, which was given to us. And rho is 100. So I'm going to write down the acceleration vector of A, which is equal to AT vector at A plus AN vector also at A. Now, this one is equal to 5 cosine 45I minus 5 sine 45j plus minus 10 square over 100 sine 45I minus 10 square over 100 cosine 45j. Now, let's look at the signs. Here, for the tangential component, we have I going in the positive direction, so this is positive, and j going downward, so this is negative. This is the angle, so the cosine of the angle is I, and the sine of the angle is j. Now, For the normal acceleration, we have, as we said, 10 square over 100. Now, I is going in the negative, and it is the sine of the angle here. So this is negative sine 45i, and we have j, the cosine of the angle, and it is minus because this component is also negative. So what are we gonna get? We're gonna get a equal to 2.83 I minus 4.24 j. The acceleration of B is very simple. It was actually given to us, which is 2I meter per second square. And of course here, I forgot, this is meter per second square. So finally, I can say that the acceleration vector of A with respect to B is equals to A minus AP, which is equal to 2.83 I minus 4.24 J minus 2 I, which is equal to 0.83 I minus 4.24 J meter per second square. If I want to get the magnitude of this one, then it is the square root of the squared component plus 4.24 square, which is going to be 4.32 meter per second square. Now, if I want to get the angle, which I'm going to call beta, then it is the tan inverse of 4.24 divided by 0.83, and this is going to give me 78.9 degrees. So, in summary, we just learned how to establish the kinematic relation for relative motion. We explained the absolute and relative quantities, and we expressed the relative position, velocity, and acceleration relation. That's it. Thank you.